go. Okay, so determine the forces in CE. Okay, first it's going to take me a minute. CE is that one. FE. FE is this one. And CD. Okay, so it's like a slice like that. Stator's dimension. Okay, yeah. Suppose a hint the force is acting at pin G. Where's G? Oh, okay. Directed along GD. Wow. Yeah. Okay. So was it? Oh, here. Let's do this. Standard view. The picture might be bigger. I can't make the. Oh, I can make the picture bigger. Okay, so let me grab. That's the wrong thing to grab it. Yes. Grab it. Oh no, I got the wrong kind of. Well, as long as I don't let up on my mouse, it'll be okay. Oh no. Well, that's okay. It'll be fine. Okay, so there's the picture, and oh, and he wanted to know this one, and this one. Is that right? Yep. Okay. But then, okay, so he's got, okay, but I got to put the forces there first. So he has 1, 2, and, oh, 1, 2, and 2. Okay, what was my 1, 2, and 2? Okay, where is it? 2,000 and then 500. So 2,000 and 500 and then 500. So what I can do is I got the picture back there again. I could work out some of that. You're kind of stuck in that. You got to find a reaction somewhere. So you got to at least find it here or here. But I think this one might be easier. Hang on. The reason it's easier is because this funny member here, it's not funny, haha, but it's this member here has got to pull on it. I'm assuming it's going to pull on this little gusset thing along its own line because nobody's putting a moment there. So then I've got to just figure out what that is. So the key is, if I want to figure out what that thing is, the easiest thing for me to do is, okay, so I know I'll have an AY and an AX, but I know I don't care. But what I'll do, I'll sum the moments about A so that my not caring is valid in the sense that now I'll just go along here. Okay, first of all, I'm going to assume that this thing is pulling. I can figure out, I can pull it anywhere I want. So in other words, what I'm saying is I'm going to assume that the gusset is pulling on the member like that. However, it's this thing can go down. Oops. Okay. I don't know what happened there. This can go down its line of transmissibility anywhere. So it can be here, up there, as long as it's in that line. So I can drop it right there. And then essentially I can say, okay, this is the structure I'm looking at. So if I want to, I mean, I don't know if it really helps much, but I could subdivide this. What I mean is, go back to here, go right here, get another snippet of it, but this time do a rectangular. Not that that matters. Oh no, I don't. I wanted to freeform this time, so I want to freeform it. I'm going to do that, and I'm just going to do that. And this time, I'll go back over here. It is there, and it's okay, but I'm going to put it here next to it. So then it becomes an official free body diagram. But I know somebody, mainly the gusset over here at G, is pulling this way. And so I don't know what to call it. So I'll call it FDG. And then I got this, okay, because this is a 4/5. This will be 4, that's a 4, that's a 5, FDG. And then up this way, it's a 3/5, 3/5 of FDG, that's a G. Okay, and I think I have all my measurements, so I have my forces here that I still don't care about. So now I'm going to take this over to this one and take it over under here. I think I still have my 2,500 and 500. So now I'll operate on this one. So I start with the A. So I got all three of these do the same thing. They go that way. So they go minus 2,000 times 10, minus 500 times 20, and minus 500 times 30. So the 2,000 times the 10, the 500 times the 20, and then the 500 times the 30. So that takes care of all those. So I took care of here, took care of this, this, and this. Not those two yet. So I'm going to go to take care of those two. This one is going this way, which is the same as the other, which is minus, okay, wait a minute, 4/5. If I make a mistake, hit me up on it, because there's the 10 foot, sorry. And then this thing, here, this thing going that way. So that's the only plus that I have. 3/5 FDG. Okay. Okay, so 2 and that's a 10, and then I got 1, 2, 3 zeros. And then I got that's 15, and 1, 2, 3 zeros. 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros, and 1, 2. So I think I get that, and that, and then these other two terms. So I'm just working on these right now. So I got 20, 10, that's 30, and that's 45. So I get minus 45 out of those. Or I move it to the other side, and I get this. Okay, wait a minute. So then FDG times, oh, I got, oh, wait a minute. Where's my moment arm? I got a moment arm here, I forgot. Did I forget that? Is that what you were about to say? Yeah. Okay. So now I'll take 30. I'll do the 30 first. 30 and 3/5 minus, I'll go ahead and do, I mean, I could clear it out, but I'm going to look that picture thing on my phone figured out. Okay, FD. Why did it change to E? Okay. Let's see if I can write good enough for it to recognize 30 and 3/5 minus 4/5 of 10. Let's see if this phone thing will figure that one out. Okay, I don't have the phone thing up, so if I make a mistake, let me know. Otherwise, I just sit in my own world up here. And that's okay sometimes. 4,500? That's what I got. That's nice and clean and comfortable. Now let me make sure it copied the right thing. I think it got the right equation right here from the picture. Okay, so now that I got that, let's see, what could I do? I could take another slice. Do I want to take a slice of this one? Maybe I do. Okay, but let me make sure. Help me. Is it? I was looking for this one, and this one, right? Was that what I was looking for? Okay. Let me get these extra things out of here. And then what I'm going to do is I'm just going to take a picture of the picture. Okay. So I'll just sweep down through here and get that. And now that we're doing sections, I mean, we don't have to do sections, but we might as well. Okay. So let's see, the simplest thing. Well, okay, first I got to put my forces. Okay, so let me do that first. Thinking to myself, wow, I don't even know which way to go with that. So I'm going to go this way, and I'm just going to go that way, and then it's going to guess that way. I'm not going to try to figure out anything. This is F, E, something or other. Is it? Okay, and this is F, E, something. What's the one? What's the node right there? Okay. Gosh, where did I go? Okay. Okay. Oh, that first one is C. Okay, so this one's the C, and that one is the F. Okay, this is the F, and this one is the F, D, something or other. It's got to be the C, right? It's got to be the C, because that's what the other one was. Yeah. So, good moment summing spots are right here, and well, I'll just start there. Okay, so right that first one, that is that right there is location C on the other diagram. So that's a location C. So what I'll do, I don't know, sum the forces about C. And then, okay, if I'm going about C, that spot right there, then this one will create a moment about it. That one will create a moment about it. And then that one. And that's it. This one won't because it goes directly down there. This one won't because it goes directly through here. And this one won't, and that one won't. So I only get 3 terms, I think. Okay, now I got to make sure I do them right. Okay, so everything's 10 feet. I'm just going to go with that. So first I made this a F. We'll start here. This one goes this way. That's a minus F, E, F, and 10. Okay. This one goes this way. That's another minus. I know that one. 500 and then a 10. Like everything is 10 on this. And then this one goes that way. Plus, okay, make sure I write this down. 3/5 of F dg. But I already found that, didn't I? Why am I writing this if I already found that? Times 10. Because isn't that the 40? That's the 4,500. So since okay, so let's do this. Okay, so 40, I can use the calculator here. And I know it's an easy thing to do. I probably should do it in my head, but my head doesn't work right sometimes. 4,500 times 3 divided by 5 is what? 2,700. So this is 2,700. Okay, 4 divided by 5 times 4,500. This I'm getting is 3,600. And this is my 45, which I'm not even going to use because I broke it into components. So that's not there. And actually, I got a white pen that can actually make it not there. Look at that. So it's not there because I just broke it into components. actually, for that mark, I can do that, which really messes with me. And this. So there we go. So now, instead of me doing that I did, I'll do it this way. Okay, so I got my 2700 spinning around. Okay. Okay, so let me make sure I got this one. I got my 500. Then I got my 2700 going the positive way, and then a 10. So I got a FEF, FEF. I can move that to the other side, and I would get 27 with an extra 0 minus 500 with an extra 0 divided by 10. I might not even need to use the picture thing here. 22, but an extra 0, and it gets clobbered. Now, is there a place okay. Okay. Wait a minute. EF. That's EF, right? This is it, right? Okay, so now wait a minute. He wanted it in kips. Look at this. Killy. Yeah, I don't like using kips. That's like, how do you do this? Wait a minute. I hit enter. What happened? Oh, you have to hit submit. Okay. All right. So at least we got that. So at least the rest is kind of straightforward. Does that make sense now? So the trick in there was that I guess what you were probably seeing is you didn't know the coordinates of that location. And so it was hard to figure out what to do unless you use that transmissibility and move it back down to D, and then you can carry it out from there. So, and we never really we don't need that. So I don't know, just looking at the rest, let's see. If that's, wait a minute, where's my picture? That is, wait a minute, that's not the picture. Here it is. There's no way to get rid of both of these two forces, the 500s. You could come down here and do E. Yeah, and then you can, yeah, this one is going to be the offset of those two. So it's going to be 22. Is that right? Yeah, 22. Got to go the other way. Oh, no, I got it. Okay. FEC's got to be 22. Let's try that. Okay. EC, 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 EC. Just remember EC, EC, EC. EC. Oh. Am I missing something? Oh, CE. Did I say 22? I don't remember what I said. 9 attempts left. Kilopounds. 3 centimeters. Enter a negative. Oh. Oh, okay. Never mind. 8 attempts left. Okay. CE, 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 CE. Oh, you know what? Duh. I forgot that one too. So it's not 27, it's 17. Duh. There's this one, there's that one. That's 1,000 and then 27. Okay, whoops. 1.7. Since I don't care, I'm just going to hit that. Oh no, check your signs, it says. Hey, it gave me a hint. How do you know how do you know when you get done with it? How many points you got? Does it say? I mean, oh, after you exit. Oh, okay. But you figured it out now, right? Yeah. Yeah, you know. Ugh. So let's hit this thing and see. I think I tried to save where I was, but I do not know. It did not save exactly where I was. So now, so what I'm doing is I'm using the PDF because the PDF I mean, the thing that I have an advantage with, I can take the PDF and write on it, like in this thing, but I can't do that to the website. So the book is actually the same. It's just listed here as page after page after page. So that's the wrong section anyway. So I got to go to the next one. I think it's the next one. Yeah. So I did a thing. It wasn't yesterday. It was Friday about the internal loads. Did y'all look at that yet? So if you hadn't, go look at that because that's going to be the stuff that's due this coming Sunday. Okay, so let me just pick out one that has goofiness to it. Okay, what I mean by goofiness is I'd like to see a moment, and I'd like to see a distributed load, and I'd like to see it shoving this way somehow. So if I can't get all those, now I think I did this one on that last video, or maybe I did that one. They're both the same thing. Okay, so I see most. Let me see if I can find a better one, but I think that one might be a good one. Yeah, that might be one of the best ones I can see. Although this one looks pretty good. Yeah, let's do that second one. Okay, so the question is, where does he want his internal loads? Oh, good, he has several different locations. So it says, determine the internal normal force and shear force and moment forces at points D and E. So he's got a D right here and E. In the overhang beam, point D, that's what he's in, is located just to the left of the roller support. So let me get a good picture of this thing. And we'll go through this because this is, let's see what I don't want a free form, I want a rectangle. I'll just grab this and go to there. Go back to here, and there's no real reason not to just do it right under here. So I'll just do it right there. Here we go. Okay, so you just want to know what D and what E is. First, we'll do E. And I don't want to mess too much with this thing, so I'm going to use this drawing. So in other words, I don't want to write on it that much. But you know what I'll do? I'll copy it twice, just in case I need to write on it. I can goof up one drawing and then use the other drawing to pull the images off of. In other words, here's what I'm going to do. Try my best to get that. Okay. Then I go down and I'm going to drop it right here. So on this, okay, so if you watched the thing last time, oops, that's not what I wanted. Uh-oh, the escape key didn't hit this. Okay. This is a positive shear. This other side is a positive shear as well on the other side. So that's the only one you got to kind of be careful of. So here's your positive shear. Here's your positive moment. And the thing is, you got to be real careful about everything as far as signs. And that's because what happens to you in mechanics of materials is those signs, this drawing becomes really important in that these are all pluses. It is possible, and then previously you were kind of taught that if you had a minus, you could flip it over. And that's true, But in this particular case, what you're going to find in the future is you're going to want to draw this and leave it as a negative sign. And that's because when you get to mechanics of materials, you'll be carrying negatives through there. So the question is, what is that? Well, the other thing is I forgot to really look at that thing. So let's look at that thing. In other words, okay. So that, it's kind of a misnomer, but that is the moment right there. Okay, this is 2 kilonewtons per every meter. So if this is 2 kilonewtons and this is 0 kilonewtons, halfway in between, it's going to be 1 kilonewton. So 1 kilonewton every running meter is the value right there. So technically what I've got to do is I've got to do this, and I'm going to use this thing again. This time I'm going to use the freeform, and I'm going to go in here and I'm going to copy it. I'm going to try to do the best I can, but eliminating that. Then I'm going to go below it, and I'm going to say, you got that. And it somehow grew a little bit, so I'm going to shrink it back down to about the same size. So this is going to be made to be equivalent to that. But how do you do that? Well, you put one load over, that is 0.5, and then a 0.5, and then a 0.5. So there's 3 divisions, and so it's a third from the heavy end, and the actual value of that force is the area of that diagram, which the area becomes 1 kilonewton per running meter times 1.5 running meters, which is the distance here, and then you've lost this area here, so you got a half of that. There we go. Yeah, I'll leave. Yeah, we'll do that. Okay. 0.5 running meters, and then a half. I think 1.5 and a half becomes 0.75, and that'll be kilonewtons. So you run down here. What did I say? 0.75. So you got 0.75 kilonewtons. That's not very much as far as an overall scheme of things. And actually, you can break this down, since that's 5 and that's 5, and this becomes 4 kilonewtons. And since that's 5 and that's 3, this becomes 3 kilonewtons. You know, the 3, 4, 5 thing. So now I could actually copy this again, and this time I would do the mode again, and this time I would just take it like so and drop it down again, probably grow again. Wow, it grew quite a bit that time. So there it is. That's what you're finally stuck with. So you had 3 modes that you had to go about there. You did the first mode where, you know, you took the beam and you're just looking at E. So I need to slice it right there. I need to either look at the left end, which is a lot of stuff to work, or I need to work on the right end. I decided to take the easy route and look at the right end. So when I did that, I took that little part copied there, but I still had a distributed load. So then I took the distributed load and made it a point load in the correct location. I broke down this into 2 components, and then I erased the main load. And so this is where I'm stuck at. And so now it's pretty easy to figure, you know, sum of the forces in the x direction equals 0 is equal to 4 kilonewtons from that, and N from that. And so N would be just 4 kilonewtons. Now I can try to erase that. That's cool because it's part of the picture. Some forces in the y. That's going to give me, oh, I should do that. Then I should do this. Forces in the y. So I get a v going up right here. I get that one going down, and I get this one going down. And so those, let's see, I got both those going down, -3 and -0.75. And so then I get v is equal to 3.75. Did I copy that thing? Oh, that's cool. That little vertical line that's sitting under the 3, that's a copy of the flashing thing. I wonder if I'd have copied it when it wasn't flashing, would it not be there? But that's, anyway. So I got 2 of them. So the last one, what you do, generally you take the point you're interested in, and then you sum. I think when you get close to the bottom of the screen with your finger, that pops up. Maybe not. Sum the moments about that point E, which is what you're interested in. And what I'll have is a -m, which is this. And then I got to start figuring out all the m's. This one doesn't produce a moment. These other 2 do. And the v doesn't produce a moment either because it's sitting at the same location. So what I get, okay, so both of them are the same way. They're both going to be this way, which is a minus. So it's -0.75 times the moment arm. And that moment arm is a third from the heavy end. So that is 0.5. And then the other one is a 3, and it's completely over there, 1.5. So what you find out is your moment is going to be equal to a -3 times 1.5, or that's, I think, 4.5. And then minus a half of 0.75. Isn't that 0.375? So the moment there would be -4.875. I don't know. I may have my math wrong a little bit. But the key is you just want to keep that minus sign. Just keep it. Just trust me. You want to keep that as a minus. You want to keep these as your positive look on the other beam. Okay, so you broke it. And so what you get is this is the same V. This is the same M. These are the same. This is the same. And this is the same. So in other words, you broke it in your brain. You didn't break it physically, but in your brain, you broke the beam in half and looked inside the internal thing. And so it just depends on which end you're looking at. And you'll just want to keep that. And that was, so if you look at last Friday's lecture, you'll see a quick, I go down to that page, which actually is right back here. Well, since I already copied the problem, I can go back to it. This page right there. So this is how they define the positives. And what you'll notice is the positives are associated with how you break it. So these are easy to remember because these are kind of the member is in tension. This is easy to remember because it sort of bends down in that fashion like that. So that's easy to remember. This one sometimes catches people, but one of the things I always look at is I focus on this and I say, okay, a positive is as if you had a cantilever and you shear it at the end. That's like a positive shear right there. And so I always look at it like that. But other people I've noticed, remember it different ways. So that's just me. In the past, during lectures, I used to come back to this to reference this several times. Usually I don't worry about referencing this one or this one because those are easy to remember. So now how do you do the second part of this? And that is, I think, okay, pardon me, but I can't remember if D was to the left or to the right. It would be uninteresting if it was to the right. So maybe I need to make it to the left. That would be the most interesting. So let's just check and see if he made it interesting. Wait, was that it? No. That's it. D is, yeah, just to the left of the roller sport. That makes it interesting. Here's why. If you're making it just to the left, you're going to have to know what the support on that roller is. Oh, that's interesting. It was further to the right of the page than I thought. So what we're going to have to do is we're going to have to do a free body diagram here, and which maybe I'll mess up with this one. I'll get my pictures off the one to the right. I'll mess with this one. So this one could have or will have some sort of support here. Call it, since I guess that's B, I'll call it VY. Then this one will have something here that will be AY and then AX. Now, I could care less about this in this problem, so it's obvious that I probably want to sum the moments there to eliminate that. And now that I've done all of this, let's see about doing something interesting here. I think you can do this. Now just move this to the right over here and start working vertically down the page there. So this is its own entity over here, and it's associated with the first, finding the internal loads at E. So at B, let's see, take off. Excuse me. So these are both pins. So what I'm going to do, I'm in search of this. The reason I'm in search of this is because I'm going to have to slice this, and it's going to have to be included. But I'm not in search of these because I don't want them. I mean, I would want them if I was building it, but since he didn't ask anything related to it, I don't necessarily want them. So I'm going to sum moments about A. Now, the first thing I got to do is I got to put, and so if you don't mind, I'll just mark up this drawing. So I'm going to take the area under this curve, which is 2 times 3, gives me 6. I'm going to do something bizarre, and I'm going to say that load is gone, except one load, that 2 times 3 is 6. And so this is weird. So I'm just going to say it's the same thing as 6 kilonewtons right there. And right there being 1.5 over. Why 1.5 over? Because it was distributed load. Now, on the second one, I'm looking for the area under this thing, which is 3 times, again, it was 2 at the left end. It was 2 kilonewtons per running meter. There are 3 running meters, so it's still 6, but I've lost half that area. So I end up back with 3. So let's see if I can monkey with this thing. Okay, so I end up back with 3. However, it looks like that's probably close to me. We're going to put it right there. Okay, so what I'll do is that'll be 3 kilonewtons. Now, this is 3 meters here, and it's 1/3 from the heavy end, which basically means that that's 1 meter. And then there's another meter, And then there's a third meter. So a third from the heavy end puts this one over. So I've taken my distributed loads, turned them into point loads at the appropriate location. Now I can start going down here. I didn't do anything with this yet, but I can start monkeying with it now. Okay, I got this one. What did I do there? What was that about? Okay, that was saying I didn't want to find the A loads. Okay, that is a negative load. 6 kilonewtons. I'm not going to include the kilos. I'm going to just say 6. It is 1.5 over from the left end to there. Then I'm going to have this BY going this way. Plus BY. And that's a full 3 meters over. And then look at this. I got just a moment just stuck right there. So I just add it. Well, okay. It's going this way. So I have to subtract it. And then I get this one. Now, I already monkeyed with this and realized that that's 5. And so this becomes 3 kilonewtons. And this becomes 4 kilonewtons. And that no longer really exists. And so now, that's actually a 4 there. Hang on. I'm going to use this one. 4. That's a 4. Okay, so this one doesn't produce a moment. But that one does. And it's 3 over. And it's producing a moment going that way, which is not in the positive direction, meaning that's the minus. It's 3 times 2, which actually is 6. So in other words, 3, this, and that gives me 6. And I think that's it. Did I forget something? I did forget something, didn't I?
6 kilonewtons in the center. That's not an actual force, is it? I thought that was the top of the triangle.
Okay, I think this 6. Well, I did forget something, but I think that's 6. Yeah, so he's saying that somebody put a moment right there. But I did forget something. Okay, so let me do an accounting here. I first did my 6, so I did that one. I did the BY. I did the 6, and I did this 3, but I forgot that one. I just completely forgot it. So here, I didn't do it on purpose. I didn't forget it on purpose, but okay, the 3, okay, first of all, the 3, this one's going this way, which is another minus, and it's 3 times, this time, that 3 is 1 meter, and then 3, and it gives me 4. Okay, so it's a 4 meters over. So now I just got to gather junk around. So it looks to me like I'll take all of these. They're all minuses. I'll move them over. So I'll say BY is equal to 6. I'll write them down complete first. Plus 6 plus 3 times 6 plus 3 times 4. And then I got to divide by 3. I might be able to do this math. 2 times 1.5 plus 2. I'm taking the 3 out. Plus 6 plus 4. I think that becomes 3, right? 3 plus 2 plus 6 plus 4. So I think I get 15 if I'm thinking right. Now, that just gets me to that point. That didn't get me where I need to go. So here's what I got now. Since I've already broken this apart, and it looks pretty ugly, maybe I could make that white marker a little bit better, but I'm just going to use that picture. I know it looks ugly, Okay, so here we go. Okay, I don't know how to get rid of some of this. So I'm just not even going to worry about getting rid of some of it. So there's my D. That, let me get another, because really I should have gone straight down. Okay, now I'll go grab the D, and then this is going to look weird. How about that? Well, I don't know. That's as good as I think it's going to get, I guess. Okay. But I guess I should have put 15 in here. So here I can make use of this and then go back and take my 15 and put it in there. So let's put my 15. Oops. Oh. Put my 15 and put it right there. So now my shear, okay, I always have to think cantilever to the right, shear goes down positive, so it's got to be negative up. If you forget, and sometimes you need reminding, let's go back. It's okay. It's not a big deal. As you go through this, you might need reminding occasionally. On a face that is left facing like this, it's going to go up. Did I do that right? Yeah. So here's my shear. Here's my normal force. And here's my moment. Okay. So to me, I always find it easiest to do the X first. Equals to 4. I get this 4. I don't get anything else. Minus N. So N's equal to 4. That gives me that. Now I got to sum. Oops. Okay, wait a minute. Let me get this straight. Sum the forces in the Y. I'll make that positive. Okay. Maybe I'll go from left to right. If I can do that. I'll say shear plus 15, right? Was it 15 or 1.5? 15. It looks like that's a point there, but that's not. That's 15. You make it look 15-ish, like that. So there, 15. Then this one's down and that one's down. I don't have another. So that's 15. Down is 3, and then down another 3. So that's 6. That gives me 9. B plus 9 equals 0, I think, isn't it? So V is equal to minus 9. Oops. So V is equal to minus 9. We're going to, well, no, we can't really make a good comparison of D of the internal loads at these two different points because they're too far away. Now, here, I'll go up closer to the diagram. We're going to sum the moments about the point. Now, that's kind of why I left the D there, because that's the point. D. By the way, I always do mine to be positive that way. If you do your positive this way, that's okay. You'll get the same thing. Okay. So first I get the moment that we're looking for. Then I might as well go ahead and include this little blue moment right here. And what's interesting is they're both going the same way. And actually, that should be negative. Minus M minus 6. It's that 6 right there that gets put right here. And now I got to do all these forces and distances. This 15 really going to slides right through D. Now, technically, if you want to be precise, you would say 15 times 0.00000, a bunch of O's, and then a 1, saying it's just to the left, which pretty much gives you 0. You're slicing just to the left of the 15, so you're including that 15 But then the 3 is spinning this way. So it's the -3. And it is 1 meter over. Remember, it's a third from the heaviest end. Is that my 3? And then I got another 3 over here. This one doesn't produce a moment about that. We got another 3 that is producing a moment that way. 3, and it's a whole distance of 3 there. So I don't know, I move this over, and moment's equal to -6, -3, -9. Let's see, that 18? So there's your moment there. Where did the rest? Oh, okay. So that's pretty much it. So all of these problems, where did it go? Oh, here it is. All of these problems kind of behave the same way. He's going to basically do something to you like, so if you look at the points, okay, so if you look at this one, you're just going to slice it here. You can see already the shear is going to be 300. The moment is going to be, okay, so the moment here is going to be -300 times 2, or 600. And then there is no normal force. So some of these are real easy. But when you get into looking at this point, and you have to slice it here, you're going to have this load. So if you've got a part of a beam that's just hanging out in space, you can just go straight at it. If you've got to go past a support member, any support member you go past, you're going to have to find that load, the By there. Well, and technically you have to find the Bx, but since there's no X force pushing on this beam, that's going to be equal to 0. And the roller is only going to have that, and AY. So this one easy. This one just a little complicated. I could actually, it might actually be less work to do this part of the beam. You know, because then I find the support over here. I can sum the moments about here and determine this load, and then work off this left end. Here, I don't have to find that. So technically, you know, unless somebody asks me some other location on the beam, so all these kind of look the same. I did that on the Friday's lecture. There's some weird ones in there occasionally, like funny looking ones at 30 degrees. I will tell you, okay, this part is left to mechanics and materials. So what you're eventually going to be learning how to do, and that's not necessarily here. Sometimes I used to cover this, but you're going to basically go through and be given a beam like this. And then you're going to find the shear diagram. That shear diagram, previously somebody may say, slice it and find me the loads right here. Well, the shear will vary through this beam based upon what's on one side or another. So the shear will change as you go across the beam. So too will the moment, and you'll see something here. Now what you're going to find, you know, this is something, you know, leave it to mechanics and materials, but what you'll find is this is linear, that's quadratic. That's constant, that's linear. This is constant, that's linear. That behaves the same way. So you'll find out that if you take this, oops, is it an X? Yeah, it's an X. Okay, sorry about that. Had to look and see. He may use X in mechanics and materials. I don't know what he'll use there, but the moment he'll definitely use. So if you look at the slope of this thing, it's positive, and that's the slope value. Slope here is negative, and that's that value. This one is quadratic, so if you look at it, you'll find a quadratic and then you'll find this. That'll be the slope that you end up with. Turns out that if you want to find, oh, and there's that thing again, you'll find out that I don't know the details completely of how it will be presented to you, but a fourth order differential equation is the beam equation where W is the deflection. And if you start taking derivatives, you'll find EI, second derivative of W squared. That's going to be your moment. And then the one other derivative, that's going to be your shear. So you'll find this in mechanics of materials that you're actually, you know, when you're actually able to come up with this, you can find out, and we will find out what this is in a few days. That's the second moment of the area projected down the end of the beam. This is something that's the modulus that, wait, you probably did have materials, right? Did y'all have materials? So y'all know what this is, right? The E, where you plot, you know, the deflection or the force and then the deflection, but it's in here, you know, stress. Ooh, that's not the stress symbol, that's the stress symbol. And then the strain, it depends on, some people list strain one of those two ways. Slope of that is the E. So you'll find out that if you can, you know, and it makes sense, the material, like if you had steel, it's 30 times 10 to the 6. If you had like in a rubber eraser, it's like really low. So if you put a load on a rubber eraser, it's gonna, the beam is gonna deflect a lot. And if you have a piece of steel, you put a load on it, it's not gonna deflect that much. So when you get your way down to it, you're basically going to determine your shear and your moment. You can basically take the load of a diagram, determine your shear, and from that determine your moment. You can actually go back to this point at this, take another diagram, so you'll have another diagram under this, and then another diagram. One of the last one will be, this one will be an angle, you know, like you'll look at the angle of the deflection, and this one will be the W. So you go from the load diagram to the shear to the moment to the rotation of the beam, you know, where it's rotating, and then from there you go to the deflection. But before you leave here and come to here, you're going to have EI in there. And so the moment is the moment, regardless of whether that thing is a piece of rubber, steel, aluminum, wood, doesn't matter. The angle, so what that is, that's a weird one there. It's basically this. You look at this thing and say the deflection does kind of like that. Well, you find that, and that's your angle. They list it that way. So in other words, you look at it, it's just an intermediary to get you to your deflection. So when you get to your deflection, you've had to go through your moment. Suddenly you go through the material, what you got, to find the slope. And then you go one more and you find your deflection. So these two are like statics. They have nothing to do with the type of material. Or okay, I got too much junk on you now. So in other words, this one and this one, and of course this one, they have nothing to do with what type of material you have. Then when you basically take this thing, and guess what? You differentiate it to go that way, you integrate it to go that way, you're integrating it again, but you include this new funny term that is associated with what type of material you have. Then you do it again and you got your deflection. So there are multitudes of ways of doing this in mechanics of materials, and he does a really good job of covering those different ways. Some of them are just direct integrations and differentiation. Other ones, there's little tricks along the way that you'll learn how to do those. So we're not going to the point where we're doing a shear diagram and a moment diagram, but be aware what you're learning here in this part when you're doing these things. I would strongly suggest you learn this section really well. How to do these different beams and how to do all these, because you will see it again and again and again and again and again. Some of the other stuff you won't see as much, but you will see offshoots of it. So you will not escape anything. And I don't have the next section, so let me just check. I think the next one is friction, I think. Yeah, next one's friction. And what I do with it is I give us the background, do a couple simple problems, because there's a lot in this that you're picking up, and that one will somewhat be in mechanics and material, but it'll be a lot in machine component and fundamental in that area. So I want to kind of make sure we understand that. But then 9 and 10, okay, so 9 and 10 in my mind should be the same chapter, but in 10, I'll just jump over it. You'll see the first thing, remember the I that sat in here? That's what that is. It's just, okay, so sometimes he'll have a subscript, but the EI, d second derivative of the deflection dx squared, and then the second derivative of this, that's the I that sat in. Oh, that's supposed to be 2. So the beam equation has to have this for you to go from the moment diagram. You have to have that I to go all the way back to deflection. If you don't have that I, you can't find the deflection of the beam given a moment. So you're going to have to know what material is there and what shape of that, what is the shape of that beam? And we'll get to that. So this one is very important. That one you picked up from, what did I just say? Material. You picked that up from materials. From statics, you're going to pick up, you're going to pick up the internal loads. And then in mechanics of materials, you'll be expected to, okay, now that you know the internal loads, I want you to know the internal load on every single point in that beam. And then you'll find there are ways that you can go about that, and you'll have to look at that. So I do have a couple of lectures on that, and I'll make them available to you. In other words, how do you do, given a beam, how do you find the V as a function of X? And how do you do the moment as a function of X throughout the whole beam? And so those are there. If you want to see them, I believe that's not, okay, here we go. I believe you can go back to, what the heck? Okay, wait. Oh, wait. Let me click it again. Click here. And then you go to, I loaded this little module called videos, and in there, they're just listed. They're just listed 1, 2, 3, 4, 5. I mean, I'm sorry I might go change those to a little bit more. If you click it, did I click it or did I not? Okay. You'll see some videos in there. So, okay, this one is finding the I, and we'll talk about that next time. How do I go back? Do I just go back and it goes back to the thing? Okay. I'll find the ones with the beams in there. Statics. This is friction. Okay, then hit this one. So it should be, okay, that was 11. Is this 10? Okay, so here's the lectures I did. This was during COVID. Okay. So here is a lecture where I, not required but may help. This is how do you find the V as a function and the moment as a function of X. So you can go through, you can see how you can map this out, make the whole thing, and then below that shear will be the moment diagram. So, and those are out there. If you, I mean, I'm just making them available. So, so I guess I'm done. And I go, oh my God. Okay, sorry about that. Did y'all have a class after this? I didn't mean to. Oh, okay. Okay, sorry about that.